Hello, I'm Amanda Clarkson, and my topic today is going to be on content and pedagogical knowledge's relevancy to student performance. The age-old question every math teacher dreads, yet has been guilty of asking themselves in their own math classes is, why do we need to know this? The public's perception of content area math teachers, particularly those in secondary education, is that they are familiar with simply the subject they teach and nothing more. This is not the case, and math secondary education majors follow similar collegiate paths as math majors. Consequently, we will be seeking what level of math content and pedagogical knowledge is really required for the most successful student achievement and how to alter the math classroom as a result. So looking at expectations of content area math teachers today, the art of teaching can be divided into two main categories: content knowledge, CK, and pedagogical knowledge, or PK. Content knowledge, as referred to by the educational researchers Ball, Thames, and Phelps, is the knowledge of the subject and its organizing structures. Pedagogical content knowledge, PCK, is a term popularized by American educational psychologist Lee Shulman, and it references the learned information regarding educational methods and includes an understanding of what makes the learning of specific topics easy or difficult. This term stems from the idea of pedagogical knowledge, or the knowledge of teaching, but with a focus on a specific subject or content. The current level of content knowledge American scholastics expects from its educators is that of whatever is in a given college's curriculum, alongside some vague additional college-level mathematics decided by a university or the state. Pedagogical knowledge expectations are that which is learned in college education courses and clinical practice, such as student teaching. So, you need a base knowledge provided by CK to then form PCK. There are three main sources for CK: teachers' own K-12 learning experiences, teacher education and professional development programs, and teaching experiences. Teachers' own learning experiences and their education and professional development programs are examples of formal learning opportunities where learning is intentional and organized and structured by institutions on the basis of learning objectives. Teachers also gain informal learning experiences when they learn by professional encounters in order to build their career knowledge through things such as student teaching. So looking at the New Jersey state standards and requirements, according to the State of New Jersey's Department of Education website, a math standard certificate in education in New Jersey requires a bachelor's degree from an accredited university, a cumulative GPA of at least a 3.0, and at least 30 credits in the math field. 12 of those credits must be in either the junior, senior, or grad level. Those are the formal education requirements from the state. Informal education requirements from the state include going through a coherent sequence of study and professional education in a provisional teacher program or an approved teacher preparation program, which ends with supervised clinical practice. So these are things like your observations, once again your student teaching, stuff like that. Aspiring teachers must also pass standardized testing, which covers knowledge deemed essential for all educators in each of the listed subjects for future teachers of all content areas or grade levels, which is called the Praxis Core. This is followed by the Praxis 2 math content knowledge, which tests the individual on number and quantity, algebra, functions, and calculus, in addition to questions on geometry, probability and statistics, and discrete math. So the purpose of the Praxis 2 is to establish that a person is proficient in the math deemed necessary to teach 6th through 12th grade mathematics. The general passing score is 160, and there are some adjustments made according to GPA. After the Praxis Core and Praxis 2 are passed, people can go on to complete their clinical practice. This includes student teaching, where student educators take part in creating lesson plans, instruction, and grading, all under the supervision of an established state-certified teacher. Cumulatively, when all these requirements are met and the clinical practice has concluded, the teacher prospect may apply for teacher certification in the state of New Jersey. So, looking at current student achievement in mathematics, many people today are concerned with student achievement in math. This can be attributed to the U.S.'s low international ranking compared to other developed nations. This ranking is measured through standardized tests such as the PISA, which is an international test given to 15-year-olds every 3 years to measure their ability to apply their math, science, and reading knowledge in a real-world context. The U.S. has continuously underperformed in the math portion of this test, with its most recent 2018 results ranking us 30th in the world in math and 25th cumulatively in education. The nation's report card found that only 25% of 12th graders are scoring at or above proficient in math. These are students at the end of their high school careers not knowing enough about the subject that they have been studying for at least 12 years to be deemed proficient. Looking at this map right here, you can see the U.S. places below countries like China, Canada, the U.K., and Germany. The PISA is not the only test to place the U.S. Lower in their mathematical knowledge. The National Assessment of Educational Progress, the NAEP, is a biennial national exam for 4th and 8th grade students that's used to compare students in one region of the country with another. 2019 results show, on average, scores mostly declined in math from 2017 to 2019, following a decade of stagnation in educational progress. The commissioner of the National Center for Education Statistics stresses that lower performing students are continuing to do worse mathematically, widening a gap in student math achievement. Focusing the lens in on New Jersey, student math achievement is actually higher in the Garden State when compared to other areas within the nation. Looking at the 2019 NAEP scores, New Jersey is one of 15 states to perform significantly higher than the national public in 4th grade math, and is one of 22 states to perform significantly higher than the national public in 8th grade math. A researcher named Ropinas Siddhabatar, in his study to find if an innovative teaching model outperformed the conventional one, actually established specific issues that contribute to this lack of mastery in student math knowledge. There are many complaints in relation to math education, a major one being that math teachers were lacking proficiency in the subject and were not conveying lessons properly to their students. With these rankings and reasonings established, it's important to decipher what exactly students are learning in their math classroom and further investigate how their teachers' abilities influence their progress. Evaluations into teacher CK and PCK reveal the deficiencies in the math classroom in relation to educators' mathematical knowledge, as it's discussed in the following slides. So researcher Murat A. Choshanov, in his 2010 study, wanted to evaluate how teachers' cognitive type of content knowledge and teaching practice align with student achievement. He first assessed the students' achievement by recording their passing rates on a state standardized test, and they assessed teachers' knowledge via a teacher content knowledge survey. Looking at the chart, you can see the study divided teacher knowledge into 3 categories: Type 1 knowledge, facts and procedures; Type 2, concepts and connections; and Type 3, models and generalizations. When this data was evaluated, Choshanov found that a significant correlation existed between the cognitive type of teacher content knowledge and student achievement. So this shows that a relationship may exist between knowledge of concepts and connections, knowledge of models and generalizations, and students' success on their examinations. To further test this relation, they also observed and analyzed 10 teachers in the classroom setting, and they performed a case study on middle school teachers' understanding of fractional division, which they once again found that to implement high-order questioning techniques that enhance the development of student conceptual understanding, teachers must possess Type 2 and now also Type 3 of teacher content knowledge. Not only that, but Choshanov reported that the higher the teacher's conceptual knowledge, the better the quality found in the delivery of a teacher's lessons. So, better delivery in a teacher's lesson also means better student understanding and success of the subject due to clearer, more comprehensive explanations and instructions. They can better navigate the complexities of the subject matter and create a roadmap that best delivers the essentials of math. This way, meeting that mark becomes much simpler. The last part of the study was a case study again, where they held a structured interview with 2 middle school teachers. Interviewers asked the educators 5 questions pertaining to fractional division. This evaluation found that, once more, student achievement is higher when Type 2 of teacher CK is possessed by the educator, this time without any links to the Type 3 of teacher CK to tie to student achievement. Although, as Choshanov writes, teacher mathematical knowledge and student achievement shows a promising positive trend, where the measure of teacher content knowledge is a significant and positive predictor of student success in mathematics. Alongside the Choshanov study, there has been further proof that such ties between teacher CK and PCK contribute to better student achievement. A 2008 study by Hill, Rowan, and Lowenberg-Ball evaluates teachers' scores on a measure of mathematical knowledge for teaching. So here they used a linear regression model to test the correlation between teacher math CK and first and third grade classes. To measure student success, students were given standardized assessments and their parents were interviewed to learn the student's academic history. Teachers were asked to fill out a structured log that tracked their math lesson content, time spent on math instruction, and instructional practices used, in addition to annually filling out a questionnaire about their educational experiences in and out of the school. Meanwhile, students' achievement was measured using this test called the Terra Nova assessment, a standardized test diagnostic system that tracks student math performance according to their grade level on a nationwide scale. The results, as seen in this chart, reveals that teachers' content knowledge for teaching mathematics, which is noted as CKTM, was a significant predictor of student gains in both models at both grade levels. Here, Model 1 was the linear measure of CKTM, and Model 2 divided teachers into deciles by their CKTM score, with the lowest decile representing the least knowledgeable teachers. It can also be observed that Model 1 shows the stronger relation between student achievement and teacher CKTM, as students scored 2.25 points higher on the Terra Nova for every difference in standard deviation in educators' CKTM. Essentially, teachers who are underperforming the most are not well versed in math negatively impact their students in a way teachers with mid-tier understandings don't. So, having access to more math knowledge across the board would lessen these negative effects. While this second study produces the same result of teacher CK and PCK playing a role in student achievement, it's a testament to how imperative it is for even lower grade teachers in elementary school to have a suitable mathematical knowledge. Possibly, early access to educators with deeper connections to math could result in greater success down the line. After all, the ideas established in these grades such as counting, place value, measurement, and shapes are foundations of the subject that reoccur in all levels of math in one way or another. Any of these findings in the Hill or Choshinov studies serve as a testament to a teacher's math CK and PCK playing an important role in student understanding and therefore student achievement. So let's take a look at what connections can currently be made from content and pedagogical courses to the teaching field. So digging deeper into my own educational requirements and experiences, specifically as a math secondary ed major at Rowan University, each course I have taken is meant to be applied to my future classroom. Some courses can be more literal and direct in their relation to teaching elementary through high school math. For instance, in college geometry, skills like proving and applying postulates are strengthened, which is often a more involved version of high school level geometry. For example, college geometry presents many proofs that could be used to explain the Pythagorean theorem as seen in this image. Such proofs are great ways to illustrate and explain the theorem that middle or high school students would otherwise be expected to memorize without deeper comprehension. I know in my own middle and high school career, I was never shown a proof of the Pythagorean theorem. Instead, I was just expected to memorize it straight on. This all simply goes to show that collegiate versions of high school classes add to teacher CK and therefore student performance through giving the teacher more ways to explain and present topics. So another example of a class like this could be linear algebra, another course found in Rowan's curriculum for math educators, and it's useful in high school classes like Algebra 2. For example, Algebra 2 requires students to be able to solve a system of linear equations. Concepts from linear algebra, like solving a system of equations by reducing in row echelon form, can be applied by the educator to quickly solve or better explain this process. In linear algebra, given the set of equations presented on the screen, one learns to quickly put the system in a matrix and then reduce row echelon form, typically using a calculator. And you can see the answers provided on the screen. A similar question can be encountered in Algebra 2, except it would be limited to two equations with two variables being solved using elimination or substitution methods. Here, having an advanced skill set acquired by a class like linear algebra is useful for educating a class like Algebra 2, as similar processes are being applied. Once again, as discovered in the studies described prior, knowing this next step into solving linear equations would prove beneficial to heightening student achievement. Students have inquisitive minds naturally, and it would not be unexpected for them to ask about what happens if the conditions of their own methodology aren't met. This is just one example of a topic learned in linear algebra that can apply to outside teaching, yet I find it explicitly reveals that even higher level courses utilize similar tools, just on a different scale. So other theorem-based courses, such as real analysis, may be more difficult for an aspiring educator to see a through line to teaching K-12 math. However, concepts discussed in this class, like how equivalence classes are obtained from congruences, can be related to a student in elementary school testing divisibility for the numbers 2, 3, 4, 5, 6, 8, 9, 10, and 11. Even in high school, teaching calc requires the educator to be comfortable explaining theorems to their class, a skill that's strengthened in a real analysis course. This is because, for example, the mean value theorem presented in Calc 1 is established on the pretense that inequalities are preserved by limits, a concept highlighted in real analysis. So, as Valerie A. DeBellis discusses in her 1997 article, Discrete Math in K-2 Classrooms, discrete math can be utilized by a teacher as soon as kindergarten. An example of this would be for a combinatorics lesson, where the teacher could ask the student to pair different shoes with different sports and see how many combinations can be made. The sports referenced in the article were tennis and bowling, with the sneakers being a pair of pink and black sneakers, so students were able to figure out that a max of 4 pairings could be made: pink sneakers with tennis, pink sneakers with bowling, black sneakers with tennis, black sneakers with bowling. Discrete math also further explains commutative, associative, and transitive properties. Other classes do this as well, and these concepts are highlighted in 6th grade math or below, where properties of numbers in reference to addition and multiplication are discussed. So, similarly, Rowan presents pedagogical courses that aim to prepare future educators for the classroom. Because of the nature of these classes, the material learned in these settings are directly tied to the context of the educational setting. So, Content Area Literacy, for example, is a class for math secondary education majors, and it focuses on promoting literacy across the content areas. Here, students learn how to write up the most effective lesson plans for their subject matter and how to best convey their topics for students at a variety of levels, such as English language learners, struggling readers, gifted students, so that they all can comprehend the lesson. Other classes in the pedagogical field aim to serve the same purpose as the one mentioned above, which is to strengthen teacher-student interaction and introduce the education major to skills applied in the teaching field. So, the list goes on with the many ways certain college-level math and pedagogical courses can be applied to K-12 schooling as it currently stands. The question remains now as to how to improve such CK and PCK to increase student achievement. So, between debates of what the curriculum should include and how educators should be presenting information, the one thing most in academia can agree on is that there's room for improvement. In the field, math educators must deliver information in a time-constrained manner. They must, as Ball describes, know rationales for procedures, meanings for terms, and explanations for concepts. Much like mathematicians, educators must be more apt to interpret student error and evaluate alternative algorithms presented to them. They must not only know that a student got something wrong, but how they had come to such a conclusion in order to fully explain and correct the error while preventing the mistake from repeating itself. Moreover, knowing ways to solve problems other than your own method is absolutely needed, as students are individuals with their own thought processes, and any sort of creativity in the math field should be celebrated. Students should not be held to mirroring or memorizing whatever their teacher does. To expect this and then devalue alternative solution paths would be detrimental. So this is where having math ed majors with curriculums mirroring math majors is beneficial, because they better understand the concepts to then better present them in their full meaning to their students. Because of this need for a mathematical specialty in the context of the classroom, having, as Hill describes, content-focused professional development and pre-service programs creates more significant gains in student achievement. So an example of this kind of program can be found in China, and author and math education researcher Loping Ma addressed in a 1999 book, Knowing and Teaching Elementary Mathematics. She studied differences between Chinese and American math classrooms in order to improve math education in the U.S. So what she found was Chinese teachers outperformed ones from the U.S. in elementary level math questions given to them, despite having less time spent in their schooling. This study, which was conducted via interview with a sample of Chinese and American elementary school teachers, though performed over 20 years ago, reveals truths that still exist in the differences between American and Chinese math education today. The U.S.'s measly 30th place math ranking on the 2018 PISA pales in comparison to China's first place position. So, what can the U.S. learn from China's math education system? For starters, know how and know why is a common phrase from Chinese math teachers. I really like this phrase. What I found is that American math teachers are struggling with knowing the why part. As Moss suggests, this can be changed through emulating Chinese schools in the three main ways listed here. So, having subject specialists in elementary school. Placing so much pressure on the individual educator to efficiently and meaningfully teach every subject at once comes at the expense of the student. Rather, by having separate teachers for separate courses, much like middle and high school is expected to do, elementary school teachers are permitted to have complete confidence in one subject they care the most about, or a profound understanding of fundamental mathematics, which is noted as PUFM, as Ma describes it throughout her writing. They can achieve higher levels of proficiency in what they are teaching. Consequently, they will also be given the chance to take more advanced math classes and can improve their and their students' understanding as a result. The most apt in math could be driven to the teaching profession at the elementary level, and teachers would be much less likely to pass down feelings of math anxiety or a specific form of test and performance anxiety when it comes to mathematics, because they truly appreciate and are knowledgeable of the subject instead of fearing it. Having comfort with the subject can eliminate this kind of intense stress behind it and ultimately alleviates the symptom of math anxiety, therefore allowing for greater learning to occur in both the teacher and their future students. Looking at the second improvement that could be made, early specialized training in pedagogy. So as I described earlier, math teachers in China go through schooling more quickly, and this is partially due to their specialized training in math pedagogy from the jump. By having college classes for math education majors in America that purposefully teach a given course and how to use this higher level knowledge for instruction in a K-12 classroom down the line, it is less likely for the connection to be severed between the education and mathematics courses aspiring teachers usually take. And the third solution Ma presents is a teaching schedule which permits more collaborative time for professional development and enhancing a refreshing math knowledge. So once in the field and on the job, it's important for math educators to never stop accumulating math CK. As an educator, you have the responsibility to both retain and grow your understanding of your subject matter, and you need time to hold constructive discourse on instruction, content, and pedagogy with your fellow teachers. While educators in the U.S. spend almost their entire workday in front of the students, Chinese educators are granted time in their schedule to study their basic teaching materials, work with students who need or merit special attention, and interact with colleagues, as Howe states in his review of Ma's book. Allotting time for professional development post-graduation allows another opportunity for self-improvement that benefits the students in the long run. Educators get to hone in on their skills, students get one-on-one time to ask questions, and younger teachers can be assisted by those who have been in the field for a while longer. So, in conclusion, evidently, there are many issues with the way schools in the U.S. educate their math teachers, along with how they deliver math lessons, ultimately causing them to rank so poorly on the international scale. As we have seen, studies repeatedly show how the CK and PCK of educators are major factors which influence student success. So it's pivotal to advance knowledge of those teaching math in classrooms nationwide today. While middle and high school math still need to be improved upon, it's most emergent currently to establish stronger math competency in elementary grade teachers, since these are the teachers who have the hardest time explaining the reasons behind math procedures. By looking to the math programs of exemplary countries like China, the U.S. can correct many of its mistakes in its deliverance of math and education as a whole through programs which allow for specialty and nuance brought back into the education framework, instruction which closely connects pedagogy and subject matter, and time set aside for personal advancement in CK and PCK with a collaboration from other professionals in the field. It's important to note that While these changes appear challenging in their application, they are proven to be effective in bringing math education into the 21st century. Ultimately, math teachers should be held to a high standard in their math comprehension, for their students depend on it. Thank you. And here are my works cited. Thank you and have a nice day.